towards the categorical Donaldson-Uhlenbeck-Yau correspondence.
Thanks a lot. Thanks a lot to the organizers for inviting me to speak here. So what I'm going to talk about is going to be largely, as Maxime mentioned, a continuation of what it's going to do, explaining a different part of what this stability program is, and so it's related to. So first of all, let me say it's joint work with. It's based on joint work with Dr. Hayden. And Maxime and Savage. And it's closely related to the other project that we have with Carlos, which is dealing with a special case of this program, but I'm not going to talk about that special case today. It's related to work with Carlos. And it's very much work in progress. So, there are a couple of papers that came out of our work so far, but I won't be talking about them today. If you're interested in seeing the sort of concrete results that came out of our project so far, you can have a look at these. But they're not connected directly, they're not the content of my talk today. This is related. Okay, so I want to explain a formalism we have started developing to address the main conjecture that Maxime described about existence of stability conditions on certain categories. So here's the plan for my talk. I want to first review very quickly the main ideas of GIT and the theory of harmonic metrics, the classical DUY, the Donaldson-Uhlenbeck-Yau correspondence. Then I want to explain an axiomatic framework for trying to formulate a Donaldson-Uhlenbeck-Yau correspondence and hopefully prove it in some cases in categorical non-commutative geometry. And then finally, we describe some applications. So before the axiomatic framework, I'll give some examples, and the applications will be applying the axiomatic framework to those examples. Okay, so what's the basic idea here? The basic idea is a very general idea in mathematics. You have some isomorphism class of objects, and you want to you want to classify some objects up to isomorphism. One way to do that is to find a canonical representative in each isomorphism class. And how do you find a canonical representative? The one way to do it, and probably the most robust and only way to do it, is to find some function on the space of isomorphism classes and try to minimize that function. So the simplest examples are, if you look at just let's say V is some finite dimensional vector space, and W is a subspace, then I can form the quotient V mod W. So the subspace W inside V defines an action groupoid, and I want to classify the quotient classifies the isomorphism class of objects in this groupoid. And you can ask, can I find a canonical representative for each isomorphism class? So finding a canonical representative is the same thing as choosing a splitting. You want to find in each coset a canonical representative. And to do this, you need to put some auxiliary structure. As we know, we can't always split a sequence of vector spaces. The auxiliary structure will be a Hermitian metric. On V, let's say this is over C. Once I have a Hermitian metric, I can split the sequence. So the picture looks like this. You have some space of cosets. I declare, so maybe I should spell out what I mean by the action groupoid. So 2 points V is isomorphic to V prime if V minus V prime is equals W and W, and W witnesses the isomorphism of V with V prime. And so, if I, how do I find this splitting? Well, on each coset, I have a function which is the distance. So you get a functional S sub V from a coset V plus W to the reals, which is just norm squared with respect to this function, dimension metric. And you minimize this function. So the canonical representative is the minimizer for norm squared. And there's another characterization of that. The minimizer is given by the critical locus of the functional, so you can compute where the derivative vanishes, and it vanishes precisely when you're orthogonal, when you intersect. So I can write it as an equation. The equation is that the inner product of the vector with any vector in W should vanish. Okay, so that's fairly straightforward. But if you take inspiration from something finite dimensional like this and you go to infinite dimensions, you often end up with something very interesting. So what's an infinite dimensional analog? We're on some C infinity manifold, and let me be compact. And I take W to be
complex or complexly?
no, just real C infinity. And let W be k minus 1 forms, and V be closed k forms. Then the analog of the kind of statement the auxiliary structure, I need some auxiliary structure to find a canonical representative. So how do I get a metric on V? I get a metric on V from a Riemannian metric. On X. And then if I follow through with this kind of game and do some analysis, you will end up with a theorem that says that k-dimensional homology classes, which is something purely topological on the left-hand side, can be identified with solutions to an equation similar to the equation that I'm orthogonal to W. And that equation is the Laplace equation. These are harmonic forms. So this is something highly, it's not obvious that the right-hand side is topologically invariant, but it turns out to be by this theorem. Now you can do nonlinear analogs of this, of the finite dimensional case. So you can have some reductive group G acting on X, some projective variety, let's say everything I'm doing is over C for this discussion. And you want to form the quotient. And as we know from, this is just a review of some basic geometric invariant theory. So if you want to construct the quotient, you can either construct the quotient stack or you can construct the GIT quotient. And to construct the GIT quotient, I want to lift this action. So lift to G action on some L, some polarization, and then I have a similar picture to this one, except that it's now nonlinear. So inside total space of L, I have the zero section, and then I have various orbits. Now I want to choose a canonical representative in each orbit. So the orbits are so I declare 2 points to be isomorphic if they're related by an element of the group G. And I want to find in each isomorphism class a canonical representative. Well, to do that I need some auxiliary structure. So the auxiliary structure will be the Hermitian metric on L. And now I can minimize, so you get a function S sub v from the G orbit to the reals, which is just S sub v is norm squared of that element. So now you can make some definitions. You can say that well, you want to minimize S, but S may not have a minimum. So you want to identify those orbits for which S has a minimum. So you say that V is polystable. Sorry, V is.
Sorry, the Hermitian metric is G invariant?
Is K invariant. So sorry. Yeah.
Oh, okay.
So where K is a compact one. So let K G equal to Kc, and Kc acts on LH. Yeah. Thanks. That's it. So now you said V is semi-stable if this S sub V is bounded below. And polystable if it's semi-stable and attains its minimum.
Local.
Yeah, actually. Yeah. And for some purposes, we are putting a factor of power. Yeah, yeah. Right. Thanks. Right. So now, if you, what this theorem will tell you is that what this analysis from before will tell you is that if you're polystable, then you can find a canonical representative up to an action of K. And so what you find eventually is that if you look at the polystable points mod G, which is more or less the geometric invariant theory quotient if I suppress algebraic geometry issues. So said theoretically, if I take polystable points modulo G, you can identify that with critical points of S up to the action of K, which is also the zeros of the moment map associated with this situation. So I won't define it. I'm sure everyone is familiar with this. Divided by K. So this theorem is the Kempfness. So again, we should expect, so this is just an analog of this very simple theorem in linear algebra when you work with nonlinear things. So now, we should again expect that when we went from finite dimensions to infinite dimensions, we had some very deep theorem. We should expect some deep theorem if we try to promote this to a theorem in infinite dimensional situations. So one situation is where so infinite dimensional analog. So let Z be some scalar manifold. And we take X to be, so E some C infinity complex vector bundle on Z. And let's take X from before to be the space of connections A with FA02 equal to 0. So FA20 is also the curvature, the 20 part of the curvature is also 0. So I have a 1-1 form and I take the curvature, which should be with a Taylor metric. And now you can identify the space of holomorphic structures on this bundle with the holomorphic structures on E is X modulo G, where G is the gauge group. Which, for example, if E is a trivial bundle, then it's just the space of maps from X to my reductive group. And on the other side, you have So this guy has a symplectic structure, which I won't write out, but you can compute its tangent space. It's just a space of one forms with values in endomorphisms, and you can wedge those together and integrate over the manifold to get a number. So this is a symplectic guy, and you can do the symplectic reduction from before, and on the other side you find Hermitian-Yang-Mills connections, which are connections that satisfy a partial differential equation. So I should say, if I take polystable guys here, polystable homomorphic structures on E, then correspond, the infinite dimensional analog of the Kempf's theorem is that these guys correspond to Hermitian-Yang-Mills connections on, and this is in quotes zeros of the moment map, which is given by curvature in this case essentially modulo the compact gauge. So this infinite dimensional analog of the Kempf's theorem is the Donaldson-Uhlenbeck-Yau. So what we see from these examples is that stability in geometric invariant theory at least is closely related to the existence of canonical representatives for some isomorphism class. That's how they arise. And one way to broadly place the goal of our project is to understand how Bridgeland stability fits into this framework. Or not really fits into this framework, but sort of what is the analog of Bridgeland stability? Maybe I should comment at this point that you can actually ask for more. So when you have an isomorphism like this, the right-hand side is a quotient in symplectic geometry, it carries a symplectic structure. And if everything happens in a Kähler situation, then that symplectic form is in fact a Kähler form on this guy. So this quotient inherits a Kähler structure. And therefore, by the same kind of argument, the space of Hermitian-Yang-Mills connections admits a Kähler metric. And therefore, the space of polystable holomorphic structures admits a Kähler metric. So really, if you want to promote this entire picture to categorical geometry, you not only want a DUY theorem, you also want a Kähler metric on the moduli space of objects in your category. So roughly speaking, we're trying to complete this analogy. You might say that you have Kähler classes in algebraic geometry are to Kähler metrics. So maybe this is part 1, and part 2 would be Kähler classes as the Kähler metrics as Bridgeland stability conditions, which are analogs of Kähler classes in non-commutative geometry. They should bear the same relation to something which you might want to call a non-commutative Kähler metric. But that's a more ambitious goal than the first question. So I'm going to focus on the first question mostly. Oh, I still have that. The end. Sorry, where? Here? Up there? Right here?
Non-commutative Kähler metric.
Non-commutative Kähler metric. So we want to sort of understand what the non-commutative analog of symplectic reduction is, if you like, which is asking what a non-commutative Kähler metric is. Okay, so that's sort of the motivation and background. Now I want to jump to, keeping that at the back of our minds, I want to jump to Bridgeland stability and try to understand it in a manner that's more amenable to being cast into that sort of framework. Okay.
So you think that only satisfying this Bridgeland stability
Well, a category, a stable infinity category over some field will be a non-commutative space, and then we can ask all the questions we asked in algebraic geometry. Okay. So yeah, so maybe you make that as a. So some examples to keep in mind. Maybe as you say, definition. This definition is just words. If I'm going to have any content for this talk, but we're always going to have a k-linear, a non-commutative space with a k-linear stable infinity category. And there are going to be two situations. So maybe for specific applications, you want to put some conditions on this category, like being complete, having enough colimits, and so on. I want to suppress that. It won't be very important today. Yeah, and there's two cases.
So K will be non-Archimedean.
Yeah, so that's what I'm coming to. So there's two cases. One is K equal to C, and the other is K is a non-Archimedean field. With evaluation with dual valuation. And the example to keep in mind is, of course, the Canonical field. So this is always the example we have at the back of our minds. And somehow most of the theorems seem to be more amenable to being formulated in the non-Archimedean case in a clean way than for some reason over C. Okay, so now I want to go back to Maxime's very first comment from his first talk that stability conditions and Fukaya categories somehow seem to be, they really go together very well. So let's look at Bridge stability from a new point of view. So let's see some non-commutative space. And suppose I'm given a Bridge stability condition, so let me call this example 0, and I'm given a Bridge stability condition which is given by some collection of semi-stable objects for every phase theta in the real line, and the central charge K0 C satisfying some axioms. Some axioms which Maxime mentioned in his talk, so I'll omit them for the moment. So I want to recast the structure in a different way. So from this category with stability condition, you get a measure mu sub e on R, a finite measure with finite support. On R for each object for each E in objects of C. So let me call this mu sub E categorical to distinguish it from the other examples. So how is this defined? For any interval I interval in the real line, the integral over I of mu categorical of E is going to be the sum of theta and I of the absolute value of Z of E sub theta, where E sub theta is the semi-stable component of phase theta of E. So that sum it's a priori looks like an infinite sum, but because there are only finitely many Harder-Nusseltmann components, that sum is really finite. So if I have any object, it has a central charge, and it has a Harder-Nusseltmann filtration, and I'm just summing over for the various phases that occur in the sum. There are finitely many points in the real line.
So what is plus mine? Theta belongs to
Yeah. It's just a finite sum. So it's nothing terribly exciting. Yeah. Well, you can say it's a triangulated DG category. Some model, your favorite model for.
But then you are
enhanced.
assuming that the residue characteristic is 0.
So far, I don't assume really anything.
Exactly the same.
And now the point is that this this measure that I defined on the real line, well, you should think of it. Well, one way to think of it, you should imagine a stability condition somehow, or at least that's how I imagine it. It's analogous to some operator on a vector space, and you think of this as a spectrum. I'll come to an example in a moment which will clarify that.
So it's like this commutative von Neumann ring and this non-commutative.
Yeah, maybe we can talk about that. That's true.
As you said, the measure.
Yeah. Now you can recover the central charge and other invariants of an object from this measure. For example, you can write the central charge Z of p is of course just the integral over r of u sub e and e to the I theta. This real line has coordinate theta. So you can recover the central charge from this measure. Okay, now what's the point of reformulating things like this? The point is that if I have a symplectic manifold and a Lagrangian in it, then I get some similar structure. So let's say L in X is a graded Lagrangian. Yeah. So the holomorphic volume form is supposed to play.
Except graded, so
The holomorphic volume form from the big conjecture about stability in Fukaya categories is supposed to give me a stability condition on the Fukaya category. But for what I'm going to say, I don't even need the Fukaya category. Let's just take a symplectic manifold and a graded Lagrangian. So then I have the argument of omega n 0 restricted to L. That's a map from L to R. Because it's graded, so I've lifted the phase to the real line. And now you have a measure on L which is given by the absolute value of this holomorphic volume form. So I can push that measure forward down to the real line. So I get mu sub L is a measure on R, and it's the push forward of the measure given by this density. And of course you can write, again, you can write the usual central charge is the integral of mu sub L e to the I theta. This is the same thing as integrating omega over L as before. Now, what's the difference from before? Earlier the measure had finite support. There's finite measure, finite support. Now this measure doesn't have finite support. It has some arbitrary support. So somehow going from, you can think of this, if you can repackage the entire notion of Bridge instability conditions in terms of this measure, then you have a generalization of Bridge instability where the measure is not finitely supported. And you can think of passing to this actual stability condition as some sort of quantization, because you started out with some spectrum that is continuous and then you end up with some finitely many values.
the main thing is a set of semi-stables,
Yeah.
not just a central charge.
Yeah, so this guy kind of tells you what it's kind of generalization of stability. It'll be there now. So let me give you a few more examples of this. Of these measures from different parts of mathematics. So Maxime already mentioned representations of curves. Q is some quiver, and then we have some representation of this quiver. Alpha in arrows of Q, and this is some complex representation of Q, and choose Hermitian metrics. So the auxiliary structure from before. So I should mention the auxiliary structure in this symplectic guy was the holomorphic volume form. Here the auxiliary structure would be Hermitian metrics on E sub v, it's HV on E sub v. And once I have a Hermitian metric, I can define an operator built out of these guys, which you saw in the first lecture today. So let's define an operator P, which is this is an operator on the direct sum of EV, and it's the sum of the Hermitian matrix on V, and I need to choose an additional piece of data, which is ZV in the upper half plane. And you can define this operator, summation ZV projection of V, sum over vertices and the sum over arrows of the commutator of T star alpha, T alpha. That's some operator. Now it's not going to be important what the operator is, but if I have some operator like this, I can, which is normal, then I can define its polar decomposition, and I get a map. So argument of P defines a map from the eigenlines of eigenspaces of P to the reals, and you can push forward norm P to get a metric, to get a measure mu sub E. So we're going to produce a measure for you on the real line. That's the second example. Okay, you're probably getting tired of the examples, but I have one more important example, and then I'll So the point in all these examples is that I'm defining this gadget, which looks a lot like something you get out of bridge instability, but I'm not defining it on the category on which we want bridge instability. I'm defining it on some category of metrized objects. For example, in this quiver example that I just gave you, the quiver had a metric on it, and associated with that was this measure. So it's some auxiliary structure that will be used eventually to construct a stability condition on the category of representation of the quiver without metrics. In the same way, for the Fukaya category example, I had some measure associated to a Lagrangian, but an object in the Fukaya category is not a Lagrangian, it's a Lagrangian up to Hamiltonian isotopy. So you can think of choosing an actual Lagrangian representing your isotopy class as metrizing the object. So you're metrizing an object in the Fukaya category, and to each metrized object, I'm associating a measure on the real line. So I'm going to do the same thing for two more examples.
Choosing good representative, what kind of main part of the story?
Sorry?
Choosing the good representative.
Yeah, that's the main part of the story. So we not only want to get a stability condition, we also want to prove a Donaldson-Uhlenbeck-Yau correspondence, which will say that the stable objects have good representatives. So we're trying to promote the features of bridge instability to this category of metrized objects, and then use that, leverage that to prove such a thing. Okay, so now let Q be a quiver again, and EV T alpha a representation, but now EV is defined over big K, some non-Archimedean field. And we have, maybe I didn't define this, so let's say OK is the ring of integers. In big K. And let's choose metrics, so choose norms. Norm V on each EV. So now I want to define an analog of this measure we had for the Archimedean case, which is on the board right on top, which came from an operator. But now I don't have, I can't define things like T star alpha, the adjoint of alpha starting from this matrix. It's not over C. So we want some analog of that gadget. So I'm going to construct an analog of that measure that we have. Okay. So the basic question to ask yourself is, if I have a representation, what's the simplest representation? I have an arrow between two vector spaces. Inside my quiver representation, I have lots of such arrows. And if I have such an arrow, what extra structure do I get on these vector spaces? So let me make a definition. Let's say EV special. So the residue field is going to be little k, and let's define EV special SP is by definition EV tensor over OK with little k. So I claim that having such a morphism gives you a pair of filtrations on both these vector spaces.
I mean, unit ball in because it's not EV, it's the unit ball.
Oh yes. So EV tilde, where EV tilde is the unit ball for the norm. Thanks. The norm. Maybe instead of EV tilde, the notation later is ED net. So this is the metrized object. Okay, so if I have this map T alpha and I have these metrics on both the vector spaces, I get a pair of filtrations. So let me define this filtration. So you get a pair of filtrations. So one is an increasing filtration. F T alpha lambda of EV, lambda in minus infinity to infinity, and a decreasing filtration G lambda T alpha of EW with lambda in minus infinity to infinity. So let me define these.
Maybe you should put special.
Sorry. So on the residue, so over little k, which could be, for example, C, I get a pair of filtrations, and the filtrations are defined as follows. So U is in F T alpha lambda of EV if and only if there exists a lift U tilde in E met of V such that the logarithm of the norm of TU tilde of W is less than or equal to lambda, and likewise U prime in is in GT alpha lambda piece of EW if and only if there exists U is in GT alpha lambda of EW if and only if there exists U prime in EV with the logarithm whose size is controlled, so logarithm of U prime of V is bigger than or equal to minus lambda, and TU prime is a lift of U. So this is some sort of generalization. If you have a pair of Hermitian metrics on a vector space, you get an R filtration. This is some generalization. You have a pair of norms on two vector spaces and you have a morphism, and you get a pair of filtrations, one is increasing and the other is decreasing. Now from these norms you can cook up a measure as before. Before I get there. So you can picture this geometrically as follows. You have your original quiver and you sort of replace it by some.
Sorry, Brown, I'm
Yeah.
confused with the last line. What does it say?
If Tu prime is a lift of U.
What is T prime?
Operator T.
U prime is some element in EV, the source vector space, which,
You have a collection.
or maybe I should put a met. Sorry, left out the met. Special. No.
Where's T?
T alpha.
It's a collection of Tau. It's just T.
So you get this pair of filtration. So you have this, your original quiver, which may look something like that. And at each vertex, so let's focus on one vertex V, I can look at all the outgoing arrows and all the incoming arrows. For each outgoing arrow, I got a decreasing filtration, and for each incoming arrow, I got an increasing filtration. So I can sort of picture that by sort of expanding this picture out and putting in an auxiliary quiver at each vertex. So at this vertex here, I get a picture that looks like this, an increasing filtration for each arrow alpha. And a decreasing filtration for each outgoing arrow. So you get an auxiliary quiver Q sub V auxiliary for each V in vertices of Q, plus a representation E V aux of the auxiliary quiver over the residue field, over little k. So we somehow reduce this situation to little k. Okay, so far we started with our quiver, we had some representation, and we put metrics on the quiver representation over the non-Archimedean field, and we got a bunch of auxiliary representations of auxiliary quivers for each vertex. So now I'm going to introduce some further auxiliary data. So for each alpha in arrows of the original quiver Q, you get, let's give ourselves a function f alpha from the reals to the reals with the property that if I look at the derivative of the function, g alpha, which is by definition f prime of alpha, should be an isomorphism from the reals to the positive. So it's an increasing convex function whose derivative gives an isomorphism of the reals to the positive.
This is like what this row that Maxine had, or analogous to.
This is going to be analogous. So this data is going to define can be used to define a Kähler potential for a metric on the moduli space of square. But I'm not going to talk about that metric much. I'm just going to say how to get a measure out of this guy, as before. And then I should quickly move to explaining what we do. Okay. So now we can define an auxiliary central charge, ZB, on this auxiliary representation to be the original ZV that we had before at that vertex times the dimension of EV plus a sum one for each incoming vertex of the filtration of G alpha times the associated period of that filtration plus the sum over outgoing vertices, the sum over lambda, minus. Of the increasing filtration associated with incoming. Okay, so where did I come up with this thing from? I came up with this formula from somewhere. So it originally came about by thinking about what happens if you take something like the Novikov field, a non-Archimedean field with a small parameter, and looking at what happens to the data you have over complex numbers as it varies with respect to a small parameter. And that's how we arrived at these formulas. But going through that calculation it's a very long story, so I don't want to explain how we came to this. Okay, so I have now a family of, now by the general theory, I have a stability condition, I have the central charge, and by the general theory, I get a stability condition on each of these auxiliary quiver categories. So when I have the stability condition, I can define this measure which came from any category with a stability condition. So we're going to define a measure now. So let's define now back to the original EV over K, big K. So we define the measure mu sub E to be the sum over vertices of Q of mu categorical with respect to the Bridgeland stability condition on the auxiliary quiver of EV auxiliary, where EV auxiliary is the auxiliary representation I have at each vertex. Okay, so I guess I have a little more than 10 minutes, so let me, yeah. Not really.
It's a joint union, yes.
The joint union of many auxiliary quiver. Okay, finally, maybe one last example, which I'll just say quickly, is the one that Maxime mentioned. So if you have some arbitrary category C defined over, let's say C met defined over OK, and let's say C, which I call C generic, is C tensor OK big K, and C special is C tensor OK little k. So this is data, input data. If I give myself this data plus a stability condition on C special, then I can again cook up a measure mu E for all E in C gen, which is defined as follows. You choose a metrization of it, mu E tilde for all C and C metrized, which is just the categorical mu for E tilde tensor OK, the residue over the, with respect to the stability condition on the special family. So I have a bunch of examples where I have some category of metrized objects, and for each metrized object I have a measure which looks like something you would get from a Bridgeland stability graph. So how do we use this to construct Bridgeland stability and prove something like the Donaldson-Uhlenbeck-Yau? So I should say that I don't know exactly how the B model analog of these things should be. Okay, so if you have this measure, what can you do with it? Okay, so maybe let me say now, in the axiomatic framework.
How do you know if you're in the A model or the B model?
The A model corresponds to the example, I had example 2, where you have a Lagrangian and you define this measure associated with Lagrangian. But in general, you'd like to have a framework, which is the axiomatic framework, which should apply whenever you can construct data satisfying the axioms. Okay, so we're given some category C, which is like the analog of the generic fiber before, and we want to construct a stability condition on this guy. And we're also given, let's say, a homomorphism, which is some central charge. Now, the idea is to introduce abstractly some category of metrized objects which maps to your category C. So this functor should be thought of as forgetting the metric. So for quiver representations, for example, this would be the category of quiver representations. This would be the category of metrized quiver representation. For Fukaya categories, this would be the Fukaya category. This would be a category where Lagrangians are honest objects, not Lagrangians are coisolative. So two different representations.
But sort of a set, no extra structure.
Yeah, I'll say what the structure. I mean,
No, I mean that not category, no.
well, these are all. When I say category now, it always means infinity category.
No, C might has any categorical.
It will have some structure. No? So this will be some category of metrized objects. Let me write f. Let's call this functor f, and let me write for f of e some object here. I'll call it e gen.
So you can keep it more.
Yeah, so that will come in the next. So I should say this framework is probably not in its final form. So it's some iteration of many things that we came at. So now you want to be able to define. Well, you want to be able to define a flow on the space of metrization. And there's a very stupid way in which you can move a metrization, which is simply to rescale it. And it's important to encode somehow that rescaling action on your category. So you give yourself a rescaling action on metrics, which is an action of the monoidal category for R with I mean, this poset gives you a category, and the monoidal structure is given by addition on an action of this category on C met, which sends a number t to an operator, a functor which I'll call RT. Which you should think of as if I have some norm on some, say, non-Archimedean vector space, or on some permission norm on a complex vector space, and this is like the norm goes to e to the t. Okay, and then you want a compatibility, which essentially says that C is the localization. So you want maps in C to be the colimit to the t of maps. Okay, so this should also remind you of how you define the Fukaya category by wrapping. That's somehow related observation.
Sorry, you imagine this T action, this R action, should I imagine as acting non-trivially on objects?
On metrized objects, but it fixes the underlying object, but it rescales the metric by, for example, if I have a vector space and a norm
I
on
still
it.
understand what the formula means then. If it kind of fixes the object and I just define R minus T of F, R minus T of F is F.
What do you mean mapping what category?
Sorry.
Oh, there must be maps in C. Well, that means R minus T map to F must be a different object if that
In the metrized category.
In the metrized
in the
category.
metrized category.
Yeah, but the underlying object is.
Very much. Right.
Yeah. So now we can define. So now we want to introduce some measure on the space of metrized objects as before. I mean, not measure on the space. Measure associated to every metrized object. So for all E in C met, we want to have mu E some measure on the real line.
For vector bundles, are maps just like maps that decrease the metric or something? Maps shouldn't see that.
So examples that satisfy this would mainly be things defined over non-Archimedean fields. So I'm not sure whether you can fit the other thing. Maybe one can fit that into this thing. So maybe I should say the main example is if you have K with a surjective derivation onto R, and for example you take C T to the R into R, and if you choose a splitting, for example you send lambda to T to the power lambda, then this will define an R action like this on the space of metrized objects by simply sending a metrized object to T to the lambda.
So I'm a little confused by terminology. Why are we calling them metrized? Why don't we call them like integral object? They seem to have this kind of
Integral, yeah.
Yeah, but if you have a in the non-Archimedean setting, if you have a model over the ring of integers, then that's the same as giving a metric.
Okay.
But we also want this to apply in the Archimedean case where
where the metric
where
is
it's
like
metric means something else.
Okay.
Okay, so you want some measure, and then you want it to satisfy some axioms, which may or may not be a complete list. Let me say that E is 0 if and only if mu E is 0. Mu is invariant under this rescaling action. Then mu of E shifted by 1. So for example, for Lagrangian, shifting by 1 is just
What was mu?
measure.
But, where in these axioms is mu?
Data.
This is
Data.
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 And-
Data of the next
This
like
data
in
will
robot.
But
plus
which of this data is mu? That's what I don't understand.
it's here, it's here.
New data.
Ah,
New data.
Maybe that's A, this is B.
One. You cut it one.
Sorry?
Nothing. Keep going.
It's A1, A2. This is the categorical data, this is the stability data, B. And so if you shift Lagrangian by 1, then that should just have the effect of shifting the measure along the real line. And finally, you want that the central charge I can define from this measure should coincide with the central charge I've already given myself. So this should equal to Z of E, which is by definition the integral of mu of E to the I theta. And then there will be some more axioms, but I guess, how much time do I have?
A couple minutes.
Okay. So you can define from this various quantities. For example, you can define the mass of an object, mass of a metrized object. So now, from now on, E is always in C-met. So mass of a metrized object is the integral of mu E over R. You can define an amplitude which measures the spread of the object with respect to, for example, a Lagrangian. You can look at how much it is spread out in phase. So the amplitude of E will be the infimum of theta, for which the support of the measure is contained in minus infinity of theta to theta plus, and minus of E similarly will be with mu. And you can define the amplitude to be the interval amp minus to amp plus, the subset of the data. So with these definitions, I can make another definition. So I should remark that the axioms imply some properties. So you have a BPS inequality. Sorry?
This says just one object at a time. There's no relationship between
Yeah,
each object.
There should be one more axiom, but it's not needed for what I was about to say. But you should have mu of, if you have an exact triangle.
Okay.
So then you have a BPS inequality which says that the absolute value of the central charge of an object, which is a purely topological thing by the other axiom. So this is absolute value of, depends only on, doesn't depend on the metric. This should be less than or equal to the mass of E. and you have triangle inequalities for mass and amplitude. Let's say that if you have an exact triangle, then the mass of E is less than or equal to the sum of the masses. And the amplitude of E is less than or equal to the amplitude. And we know that the categorical BPS inequality is saturated precisely for semi-stable objects. So the idea is to start with some arbitrary metrization of your object and try to modify that metrization till you minimize it, and then you hit a semi-stable guy. So let me just make a definition.
Can I ask how confident are you that 2 is the right axiom? 2 says that when you rescale, the mass doesn't change. The measure doesn't change.
Yeah.
I find it very surprising because it tells me that if I have a Lagrangian and another Lagrangian and try to cancel them out by taking a cone, it's immediately 0. Not that once you flow it to the 0 object, it becomes 0.
No, but
Maybe should we-
it's not a geometric flow, it's a flow of a constant and a tangent. On the nose.
Okay, thanks.
Okay, so since I'm out of time, let me just quickly make a definition and then state what the claim is in general. So, the definition: a metrized object E is harmonic of phase theta if the amplitude of E equals just the singleton theta, the support of that measure. And so the idea is, the claim is that if you have one more axiom, which, okay, now I've written this. So maybe I'll just say in words, the idea is that you start with some arbitrary metrization, and there are two approaches you could take. You can apply a flow to reduce the mass of that object, or you can apply a minimizing sequence to that object. And if you can show that when you bound the mass and the amplitude, first of all, that the flow or the minimizing sequence decreases the mass and the amplitude, and that when you bound the mass and amplitude, you get a compact space, then you can hope to find to converge to some harmonica. So the claim is that if you have control on this compactness, if you have mu E for all E plus control on compactness, then you get a stability condition on C gen with C gen polystable of phase theta being the same thing as harmonic, can be identified with harmonic objects, harmonic metrized objects of phase theta.
So this compactness means that you have a minimizing sequence, it's always
Yeah. So this is the framework that we use to. So Maxime mentioned in his talk that we can prove this DUY theorem in two scenarios. One was the example, I forgot the numbering now, example 5 and the non-Archimedean quiver case. And in both those cases, this is the framework that's used to prove it. It's not a theorem in general, it's a claim in general, but it's a theorem for these two examples. So I'm out of time, so I'll stop.
Any quick questions or comments?
How do you define? Remind me again what in the Lagrangian case. What am I supposed to imagine this measure to be?
So you have this argument function.
Yeah. Yes.
Or you have given some omega in 0. This maps L to R, and you want to push down. So to get the mass of a Lagrangian, you would integrate the absolute value of omega in 0, this density over L. But instead of integrating over L, I can first push forward this measure to the real line and then integrate. So you just take the push forward
You basically take the volume of the level sets
of the level set. Exactly. Yeah. And the point is somehow that this measure is now no longer finitely supported, but
Yeah.
so on the metrized objects
but-
you have some
But
continuation.
else compacting.
Yeah.
Do you have any D-model examples?
P model, not a direct one at least, which maybe through some indirect mirror symmetry or something.
So about A now.
Yeah.
Yeah, I understand. But that's my question.
Okay, so left hand quantum again.